Good evening, everyone. This is the fourth live session for polymer reaction engineering. We will be solving some sample problems to help you solve the assignment for this week. My name is Rohan Jadhav, and we will be proceeding with the live session now. So, in this live session, we will be discussing about reactors and reaction schemes, multiple reactions in series or in parallel. So, moving on. First question we have for the recycled reactor, select the incorrect options. So we'll be looking at these options one by one and figure out which one of them is incorrect. So starting from the first one, we have the product stream is split and returned to the entrance of the reactor. So we have a schematic right here. So we have a schematic right here, which shows how uh, what is happening in a reactor and how the recycle stream functions. So we have an inlet stream right here and we have an outlet stream right here. So what happens here is that uh, here some volume of the reactant enters the reactor, reaction occurs, and then we have some product as outlet. And at the outlet, we are having a division of streams. We obtain the product right here, and then one stream is sent back to the inlet. Now this is your recycle stream. So the product stream split here into two parts, and one is returned to the entrance of the reactor. So first first statement is true as it describes the function of the recycle stream. Next we have conversion of the reactant is decreased due to the returning of the product stream to the entrance. Now for any reaction there is a conversion rate. So conversion rate for many reactions is not actually 100. It's not 100% conversion. So what happens is some of the reactant is unreacted. So in the outlet stream, the composition of the outlet will be some some of it will be unreacted reactants, and some of it will be the products. So what happens is when you send back the recycle stream to the inlet, the unreacted uh, unreacted reactants react react to the inlet stream inside the reactor, and then the product is formed. So the conversion of the reactant does not affect it does not get affected because of the product stream returning back to the entrance. So this statement is false. Third one, we have the recycle ratio can be defined as the ratio of the volume entering the reactor at the entrance of the reactor to the volume leaving the reactor system. What we have here is that we have an inlet stream. You can take its volume, and we have an outlet stream with a certain volume. If you were to draw a volume balance for this or a mass balance, you would see the balance should show that inlet should be equivalent to the outlet. Now, since the outlet stream is getting divided into two parts, as one part is going to the recycle stream and the other comes out as the product, the recycle ratio can be defined as the ratio of the volume entering inside and what is exiting outside. Uh, because of that ratio, you will be able to find out that what percentage is being sent back as recycled. So this statement defines the recycle ratio, which is correct. And next we have if recycle ratio R is infinite, then the recycle reactor approaches to the mixed flow reactor, and the performance equation of the recycling reactor will become the same as the performance equation of an MFR. Now, what happens in this case is that as we just defined the recycle ratio, if the volume entering the reactor is, for example, X, and the volume coming out uh, for for the recycle ratio to become infinite, the volume coming out should be basically zero, so that the entire terms become infinite. The recycle ratio becomes infinite. So here, in this case, what happens is the entire stream is being recirculated again back inside the reactor. Now, when this happens when you have a mixed flow reactor right here. You can see that whenever we have an inlet stream, all the reactants and products are properly and uniformly mixed inside. Okay, so that's why if the recycle ratio is infinite, then a recycle reactor approaches mixed flow parameters, and that's why performance equation of a mixed flow reactor will be applicable to it. Next, we have for irreversible parallel reactions, A giving R, which is the desired reactions with rate constant K1, and next A giving S. These are parallel competing reactions occurring at the same time, where A is disappearing and forming R and S. And here S is the undesired product, and its rate constant, the reaction rate constant is K2, and in first case it's K1. The rate of disappearance of reactant A can be written as. We all know that rate of disappearance of A is equivalent to the formation of the product. So in that case, we can write it as like this: Cr by dt with respect to time. We have K1 for formation of R with the order of reaction. Next, we have Ca by dt, K2 Cs with some reaction constant. Sorry, some reaction order right here. So we have two different rate constants for two different reactions occurring parallelly and competing with each other, where R is our desired product and S is the undesired one. So if you add these two expressions, what you get is K1 plus K2 times Ca. Since A is the one which is getting consumed and K1 and K2 are the rate constants of the reactions occurring simultaneously. Addition of these two expressions will give you this, and this is option number 4. So this is the answer to this question. As the rate of disappearance of reactant A can be written in terms of the sum of the two rate constants of the parallelly occurring reactions multiplied by the concentration term. Next, we have if the recycle ratio R is 0 in a recycle reactor, then the recycle reactor approaches to plug flow reactor, and the performance equation of the recycling reactor will become the same as the performance equation for the PFR. Now, what happens in PFR is that we don't have any recycle coming back. We basically don't have any recycle coming back, and all of it passes through. So what happens is if the recycle ratio R becomes 0, it means that when would this happen? This can happen when the inlet is very low or the outlet is high enough. So in that case, the entire term approaches to 0. So in that case, the reactor behaves as a plug flow reactor. So that's why the performance equation for a PFR will be applicable. So it is true. The recycled reactor will behave as a plug flow reactor. So the next question we have: choose the correct option for multiple reaction systems from the following statements. Statement 1. For multiple reaction systems, there is a need for minimization of undesired products and size of the reactor to maximize the desired ones. Statement 2. For multiple reaction systems, there is a requirement of more than one rate expression to describe its kinetics. As we have seen in the second question right here, that a complex reaction such like this, uh, where there are two reactions occurring simultaneously and competing with each other, the rate constants are different right here. So we do need two different rate expressions to describe the entire reaction where the reactant is getting consumed. So for multiple reaction system, the requirement of more than one rate expressions is necessary to describe its kinetics. So that's why statement 2 is true. Then moving on to the first statement. For multiple reaction systems, there is a need for minimization of the undesired product and size of reactor to maximize the desired one. Now, there are two parts to this statement. First is need for minimization of the undesired product. When we have a reactant which is getting consumed to form a product which is desired one and the undesired one, it is always favorable to have a higher conversion rate for the product, so that your more of the reactant follows this reaction route rather than going to uh, give this undesired. So minimization of the undesired product is always favorable. So this part of the statement is true. Next, we have size of the reactor to maximize the desired mix. Now, if minimization of the size of the reactor, if the reactor is really big, the residence time will increase, and if residence time increases, there is more possibility for the formation of this product, undesired product. And that's why with the small reactor volume, we can make sure that the amount of undesired product being formed is less, and the product stream product stream will be rich with the desired product. So that's why statement one is true and statement two is also true. Next, we have for different types of multiple reaction systems, select the correct statement. There are four statements here, and we'll be going through one by one, and we will see which one of them are correct. In a parallel reaction system, the reactants are consumed by different reaction pathways to form different products. Now, in a parallel reaction system, so here the schematic shows the parallel reaction system. You have A as your reactant, which is forming B and C, with K1 and K2 being the rate constants for the different reaction schemes of our B and C. So the reactants are consumed by different reaction pathways. So you can see that it might be possible that the formation rate of B might be faster than C. So the consumption of A towards formation of B will be faster than C, and that's why the reactant consumption will have a different reaction pathway to form different products. Second statement we have in series reaction systems. The diagram right. This reaction scheme right here shows you the series reaction system. The reactant is consumed to produce an intermediate product which reacts further to produce the final product. So it is evident here, right, that A is getting consumed to form B, and then B converts to C. So B is an intermediate product since it's the middle point where from where onwards C is formed. First, it's like the reactant starts from a certain energy level, then it rises to the intermediate, and then it comes back down to the product. So the reaction scheme itself will be divided into two parts, A forming B and B forming C. And the kinetics for these reactions will be different with different rate constants right here as shown. So that's why this statement is correct. Then the third one is in a complex reaction system, both parallel and series reactions are involved. Yes, in a complex reaction system, it can be defined as a reaction. A complex reaction can be defined as like uh, a reaction having many reactants with different kinds of product formation schemes, as they as each reactant can have competing reactions or simultaneous reactions, or the reactants themselves can react with each other and undergo series reactions. So it can be defined as a complex reaction system. And yes, both can be either parallel or series. Series and parallel reactions will be involved. So since all the statements are true, all of the above will be the correct. Next, we have to obtain the desired product. In case of a parallel reaction system, the concentration of the reactant to be maintained at a low value is done by using a mixed flow reactor, maintaining the low conversion rate constant, or none of the above. So, starting from the first option, what we have here is using a mixed flow reactor. Now, what happens in a mixed flow reactor is the moment you feed it the reactant, it instantly undergoes homogeneous mixing, and because of this homogeneous mixing, it starts reacting quickly and starts forming the product. So the concentration decreases rapidly the moment it undergoes reaction right here. So in a parallel reaction scheme, if you introduce the reactant inside, it will readily start reacting and start forming your uh, desired product and the undesired product. So what happens here is that the concentration of the reactant is to be maintained at a low value by using mixed flow reactor. Now, since the concentration decreases rapidly the moment it is introduced inside, Mixed flow reactor scheme is very suitable for keeping keeping the concentration of the reactant at a low value to form the desired product. Because the moment it starts reacting in your outlet stream, you will see that your desired product will be higher than your undesired one. Maintaining low conversion. Now, uh, is maintaining low conversion is difficult, as you can see that in parallel reaction schemes. Uh, in parallel reaction schemes, the conversion for the uh, conversion for either of the reactions can be more or less, because of which the controlling of the conversion rate can be difficult. That's why using the mixed flow reactor scheme is a better option. Moving on to the next question, we have for selectivity parameter SRS, that is defined as SRS equal to rate of formation of R by rate of formation of S is equal to dCr by dCs, forming giving rate constant for R reaction scheme. Let's make it one, and then for reaction two we have two, and we have consumption of A and order of the reaction. Now, order of the reaction here uh, will differ, as R is the desired product and S is the undesired product. And since the reactant is decomposing to form these two with different rate constants, the it it is possible that they might proceed with a different order of the reaction. So let's name them A1 and A2. So consumption of A will proceed with both of the reaction orders being added as the reaction proceeds. So, how do we control the formation of desired product R? So, if the reaction rate for the first scheme is higher than the reaction rate for the second scheme, it means that since the reaction, sorry, not reaction rate, I mean the order of the reaction is higher than the order of the reaction for the second scheme. Having a higher order indicates that the concentration sensitivity of A and R is very high. So because of this, it is necessary uh, that we maintain a low concentration of A at the initial point so that the formation of R is controlled. And since it is having a higher order of the reaction, the sensitivity is high. So a small amount of A will readily undergo reaction to give the desired product R. And since the order of reaction for the undesired product is low, we can safely assume that small amount of reactant A will be favorable more to form R than S, and that's why uh, using mixed flow reactor would be a better scheme, as we have discussed in the previous question that the moment you introduce the reactants, the concentration drops to zero as the uniform mixing starts forming the products instantaneously. In a plug flow reactor, what happens is as the reactant is introduced, its concentration does not drop to zero instantly. It excuse me. It gradually reduces over the length of the plug flow reactor. Excuse me. Keeping the ratio of RR by RSI as possible. Now, this ratio of R and RS can only be kept high by using the mixed flow reactor, as we have just discussed in the previous question that decreasing the concentration of A, and since the order of the reaction for A forming R is higher, the concentration sensitivity is very high for formation of R. So a low quantity of A will be sufficient to give desired product. Moving on to the next question, we have for quantitative analysis of series reaction systems. Let's set an example right here. Excuse me. Uh, Here we have a series reaction, A giving B and B forming C with different rate constants. So for analysis of series reaction system, the maximum intermediate can be formed if fluids of different compositions and stages are not allowed to mix. Now, we need maximum amount of B formation. So it would be suitable, what the statement says is, if the fluids of different compositions and stages are not allowed to mix. If, uh, as the reaction proceeds inside the reactor, if the streams of A, which is getting converted to B, and B, which is getting converted to C, if streams of A and C are mixed, there is a good chance that formation of intermediate might not take place. It might reduce because uh, formation of the product C might hinder the uh, formation of A to B. Because of this, the stream mixing might divert divert the conversion of A to B and slow down the conversion rate. And because of this, it is suitable that A is given the initial conditions for its consumption to form B, and that's why uh, it is true that if compositions and stages are not allowed to mix, we can have maximum amount of intermediate. Because the initial conditions to form B might be different for A, and if C stream is interfering with A, this might cause hindrance to form B. Then we have the last question. For selectivity parameter, we have SRS, again the same expression with the different rate constants. As you can see right here that this is the expression for selectivity parameter and to control the formation of the desired product R, which is correct, for A1 and A2. Now in this case, both formation of R and your undesired product B, product S, is having a similar order of reaction, which means that the concentration dependence of R and S on A is similar. Means there is an equal chance of formation of R and S no matter no matter what kind of reactor you use or what kind of conversion scheme you keep, because product distribution becomes independent of reactant concentration since they both are following the same order of reaction. And next is unaffected by the type of reactor, because even if you mix it uniformly and drop the concentration drastically in the initial stage itself, or if you make it flow through a plug flow and gradually decrease the concentration, it won't matter since both of them are following the same reaction order, and that's why they will be unaffected. And so both A and B uh, are correct. Following a similar question, we have a third case for this same reaction scheme where the formation of desired product R, which is correct for A1 is less than A2. Now, in this case, what happens is our desired product is falling behind because it is having a lower order of reaction than your undesired product. Now, in this case, what should one do to maximize the formation of your desired product? We can first statement is keep the concentration of reactant A as high as possible. This might create problems because since the order of reaction of the undesired product is very high, it has a very high dependence on concentration of A. Because of this, if you keep the reactant A, concentration of reactant A as high as possible, this might backfire and the outlet stream can produce like very high amounts of undesired products. Because of this, this is false. This is a wrong scheme because concentration of reactant A would only help in formation of the undesired product. Next is by using a plug flow reactor. Now, in a plug flow reactor, what happens is the concentration reduces gradually as the time goes. Now, as time goes, we are giving, since the concentration is reducing gradually, and since the order of the reaction for the undesired product is higher, it will give S more time as the concentration is reducing gradually to form and reactant A to decompose and to react and form the undesired product. Next, we have by using a mixed flow reactor. Now, in a mixed flow reactor, what happens is that the concentration of the reactant drops drastically the moment it enters inside because the contents are mixed together thoroughly the moment they enter inside, and that's why the reaction rate, the reactivity inside this reactor is high since it's continuously stirred. So in that case, what happens is if we use a mixed flow reactor, A will decrease rapidly, and this will hinder the formation of your undesired product. And since it is stopping the formation of undesired product, there is a good chance that some of the outlet stream will contain your desired product. Because since the reaction order for the second reaction is higher than the first one, it is necessary to stop the second reaction than to favor the first reaction uh, because of the circumstances, the selectivity for the second one is higher than the first, and that's why using a mixed flow reactor is a good choice. Thank you very much for attending this session, and you can drop your questions in the online forum for any discussion, and we might get back to you and answer your questions. Thank you.